Hello everyone, this is John Hashmat and welcome to Physics Simply. In this video I will be solving the paper 4 exam for May-June 2023 variant 2. So let's get started. Question 1a says figure 1.1 shows a helicopter which is stationary at a height of 1,500 meters above the ground. State the two conditions necessary for the helicopter to remain in equilibrium. That would be no resultant force and no resultant moments, or clockwise moments equal anti-clockwise moments. Part I says the mass of the helicopter is 3,200 kilograms. Calculate the change in gravitational potential energy of the helicopter as it rises from the ground to 1,500 meters. So the change in gravitational potential energy is equal to mg delta h. So we have the mass 3,200 multiplied by g, which is 9.8, and by the height, which is 1,500 meters. This gives an answer of 47,040,000 joules, which we can approximate and write in standard form as 4.7 times 10 to the power of 7 joules. Part B of the question says figure 1.2 shows a vertical speed time graph for a parachutist who jumps from a stationary hot air balloon. The parachutist jumps from the balloon at time equals 0 and reaches the ground at B. The point A indicates when the parachute opens. On figure 1.2, label a point on the graph where the acceleration is 0 with 1. So we have two ports that we can call 1, which are the horizontal lines. That means there is no acceleration. The second request is acceleration negative with 2. So acceleration negative is only one part here, which is the decreasing speed part. The last request is decreasing acceleration, which we can represent here or here. But the question requires a point for each case, so you do not have to mark all the areas, just one for each. Part I says explain in terms of forces the changes in the motion which occur from when the parachutist leaves the hot air balloon until point A. So this is before the parachute opens. So at the start, only the weight acts on the parachutist. So acceleration is equal to gravity acceleration. Then we say that as speed increases, air resistance increases, so the resultant force and acceleration decrease until the weight is balanced by air resistance, so resultant force and acceleration become 0. That's why the speed becomes constant. Question 2 says a student catches a cricket ball. The speed of the ball immediately before it is caught is 18 meters per second. The mass of the cricket ball is 160 grams. Calculate the kinetic energy stored in the cricket ball immediately before it is caught. So kinetic energy is equal to half mv squared. So half multiplied by the mass, but it should be in kilograms. So we divide 160 by 1000 to convert it to kilograms, and then multiplied by the speed 18 squared. This gives a value of 25.92, which we can approximate to 26 joules. Part B says it takes 0.12 seconds to catch the ball and bring it to rest. Calculate the average force exerted on the ball. We use force is equal to the change in momentum over time, which is equal to mass multiplied by the change in velocity over time. Substituting, we have the mass, still we need to convert it to kilograms. Then the final velocity is 0, the initial velocity is 18 from the previous part, divided by the time 0.12 seconds, which gives an exact value of 24 newtons. Part C says as the student catches the ball, she moves her hands backwards. Explain the effect of this action on the student's hands. So this increases the time of the impact and decreases the force of the collision. Question 3a says figure 3.1 shows a person moving across an ice-covered pond to reach a ball on the ice. Explain why this way of moving across the ice is safer than walking. Use your understanding of pressure in your answer. So we say that the weight is spread or distributed over a larger area, so pressure decreases and there is less risk of the ice cracking underneath the weight. Part B says figure 3.2 shows the side view of the pond with a layer of ice floating freely on the water. The surface area of the pond is 5 meters squared. The mass of the ice is 690 kilograms. The density of the water is 1000 kilograms per meter cubed. Point X is 0.45 meters below the ice, that's inside the liquid. Calculate the pressure at point X due to the ice and the water. So we need to calculate the total pressure of two things. So we say that the total pressure is equal to the pressure due to the ice plus the pressure due to the water. For the ice, that's a solid, we can use the equation force over area. And for the water, that's a liquid, we use rho GH. Now we calculate. So the force due to the ice is the weight of the ice, which is equal to the mass multiplied by the gravity field strength. Then we divide it by the area, which is 5.0. That's the first part. Then we add the pressure of the liquid, which is the density 1000 multiplied by the gravity field strength 9.8 multiplied by the depth, which was 0.45. That gives a total answer of 5762.4, which we can approximate to 5800 or 5.8 times 10 to the power of 3, and the unit for pressure is Pascal. Question 4a says the temperature of a fixed mass of gas at constant volume is decreased. State and explain in terms of particles how the pressure of the gas changes. So we say that particles lose kinetic energy or move slower, so they collide less frequently and with lower momentum, so pressure decreases. Or we can say that the force decreases, so pressure decreases. Part BI says state the value of absolute zero in degrees Celsius, that's negative 273, that's 0 Kelvin. Part I says explain what is meant by the term absolute zero, refer to particles in your answer. So this is the temperature at which particles have no kinetic energy or not moving. Part C says cylinder 1 contains 350 centimeter cubed of gas at a pressure of 9.0 times 10 to the power of 4 Pascal. The gas is transferred to cylinder 2 and the pressure increases to 1.6 times 10 to the power of 5 Pascal. The temperature remains constant. Calculate the volume of cylinder 2. So we use P1 V1 is equal to P2 V2, or the pressure multiplied by volume is a constant. And we have the initial pressure 9.0 times 10 to the power of 4 multiplied by the volume 350 is equal to the final pressure 1.6 times 10 to the power of 5 multiplied by the unknown volume. So we divide by 1.6 times 10 to the power of 5. V2 would be 196.875, which we can approximate to approximately 200 or 197 centimeters cubed. Question 5a says figure 5.1 shows an electric heater used to heat a room. The dimensions of the room are 4.5 meters times 6.1 meters times 2.4 meters. The density of the air is 1.2 kilograms per meter cubed. Show that the mass of the air in the room is 79 kilograms. So mass is equal to density multiplied by volume. So we multiply 1.2 by 4.5 by 6.1 by 2.4, which are the dimensions. So this part is the volume. This gives a value of 79.056, which is approximately 79 as required in the question. Part I says the power of the heater is 1100 watt. The specific heat capacity of the air is 1000 joules per kilogram degrees Celsius. Calculate the time taken to increase the temperature of the air in the room from 16 to 20 degrees Celsius. So we use Q is equal to mc delta theta, or we replace Q, which is the thermal energy, by power multiplied by time, and then we say it's equal to mc delta theta. We want the time, so we divide the mass and C and delta theta by the power. Substituting, we have the mass, which was 79.056 by 1000, which is the specific heat capacity, and then we calculate the difference in temperature between 20 and 16. Then we divide by the power, which is 1100. That gives a time of 287.47636, which we can approximate to 287 seconds or 290 seconds. Part III says, suggest one reason why the time calculated in AII is the minimum time needed to increase the temperature of the air in the room. So if we need more time, that means that we are losing heat. So this is due to heat lost to surroundings. Part B says, figure 5.2 shows a cross-section of a double glazed window in the room. State the main methods of the thermal energy transfer from the room to outside, which are reduced by this type of window. So this type of window traps air inside this gap, so it reduces convection and conduction, since the trapped air cannot circulate and it is a poor conductor. Question 6 says, two types of seismic waves are P waves and S waves. State the types of wave that P waves and S waves can be modeled as. So P waves are longitudinal and S waves are transverse. Easy to remember, there are S's in transverse, so they represent the S waves. Part B says the velocity of a P wave in the Earth's solid crust is 7.2 kilometers per second and its frequency is 4.5 Hertz. Calculate the wavelength of this P wave. So lambda is equal to V over F, the speed divided by the frequency, but we need to change the speed into meters per second, so 7.2 times 10 to the power of 3 divided by 4.5. That gives a value of 1600 meters. Question 7 says, figure 7.1 shows a container of oil. A ray of light shines on the surface of the oil. The refractive index of the oil is 1.47. Part A says, on figure 7.1, draw the normal at the point where the ray enters the oil. So we use a protractor to draw 90 degrees from the point where the ray meets the surface. And we use the protractor as a ruler to draw the line. But we draw it as a dashed line to represent that this is not a real ray of light. Part B says the angle X is 56 degrees, but the angle X is not the angle of incidence. This is the angle of incidence. So first we calculate the angle of incidence, which is 90 minus 56. That gives an answer of 34 degrees. Calculate the value of the angle of refraction in the oil. So we use the equation of the refractive index. Refractive index of a medium is equal to sine the angle in the air divided by sine the angle of the medium. So substituting, we have 1.47 is equal to sine 34 over sine the required angle of refraction. So by replacing these, we have sine the angle of refraction is equal to sine 34 divided by 1.47. Then we use shift sign answer on the calculator, or we calculate the inverse sine of this part here, which gives an angle of refraction of 22.358668, which we can approximate to 22 degrees. Part C says state the approximate speed of light in air. This is 3.0 or 3 times 10 to the power of 8 meters per second. Part D says calculate the speed of light in the oil. Give your answer to 3 significant figures. So we use the other equation for refractive index, speed in air over speed in the oil or the medium. So 1.47 is equal to 3 times 10 to the power of 8 divided by the unknown speed. So we replace these two. So we calculate 3 times 10 to the power of 8 divided by 1.47. This gives a speed of 204,081,632.7, which we can write in standard form as 2.04 or 2.0 times 10 to the power of 8 meters per second. Question 8 AI says state what is meant by magnetic field. It is the region where a magnet, a magnetic material, or a moving charge experience a force. So either one of these would experience a force in a magnetic field. Part double I says define the direction of a magnetic field. It is the direction of the force on a free N pole or north pole placed in the field. So if you place an N pole, it would move in the direction of the field. Part B says figure 8.1 shows a negatively charged metal sphere. On figure 8.1, draw 4 lines to show the electric field and its direction. So for a spherical object, the field would be radial. So we have 4 lines pointing towards a center. And for a negative charge, the field would point inwards towards the center of the sphere. Part C says figure 8.2 shows a circuit. We have 3 cells with a voltmeter connected in parallel, a resistor in series with 2 resistors R1 and R2 in parallel, and a diode connected to R1. The 3 cells are identical and have 0 resistance. The resistors R1, R2, and R3 are identical. The reading on the voltmeter is 6 volts. When the diode is conducting, it has 0 resistance and 0 potential difference across it. Part I says determine the EMF of one cell. So the total voltage was 6 and we have 3 cells, so we divide 6 by 3, which gives 2.0 volts. Part double I says determine the ratio of the potential difference across R2 to the potential difference across R3. So if we take a value for the resistance and they are all identical, so this is 1 ohm, 1 ohm, and 1 ohm. This part here would have a total resistance of 1 times 1 divided by 1 plus 1, which gives a resistance of 0.5 ohms. So the parallel section has half the resistance of R3, and these are connected in series, so half the resistance takes half the voltage, or double the resistance takes double the voltage. So R2 to R3 is a ratio of half to 1 or 1 to 2. So this is the answer. We write 1 to 2. Part triple I says all the cells are reversed. State and explain the change in the current in R1. R1 was connected to the diode, which allows current to flow in one direction, and reversing the battery would cause the current to flow in the opposite direction, so the diode will not allow it. So we say the diode is connected in reverse, so current is 0. Part 2 says determine the new value of the ratio of the potential difference across R2 and R3. So now R1 is not working, so we don't have the parallel connection. Now we have the resistance 1 to 1, so the voltage would also be divided with a ratio of 1 to 1. So this is the answer. Now, since the resistors are identical, the voltage would be identical or divided equally across the resistors. Question 9a says table 9.1 shows some properties and values of alpha, beta, and gamma radiation. Complete table 9.1. So first we have the number of protons. For alpha and gamma are given. For beta it is 0. There are no protons in a beta particle. It's an electron. Number of neutrons for an alpha particle is 2. It has 2 protons and 2 neutrons. For a gamma ray, it has no protons. It has no particles. It's a wave. As for the charges, the gamma radiation has no charge or no net charge. For the beta, it is a charge of 1 electron, and alpha, it is a charge of 2 protons, and the charge of a proton is equal to the charge of an electron. So as a value or as a number, the charge of the electron is half the charge of the alpha particle, so we divide that by 2. That gives an answer of 1.6 times 10 to the power of negative 19. And an electron is negatively charged, so it is negative 1.6 times 10 to the power negative 19. As for what it is stopped by, for an alpha particle and beta particle, they are given. For gamma radiation, we need to use thick lead or concrete. Part B says state how beta decay changes the nucleus of an atom. So 1 neutron changes into 1 proton. Part C says a radiation detector used in a laboratory detects a background count rate of 30 counts per minute. The radioactive source is placed in front of the detector. The initial reading on the detector is 550 counts per minute. The half-life of the source is 25 minutes. Calculate the expected reading on the detector after 75 minutes. So we have the half-life and the total time. we divide the total time by the half-life to get the amount of half-lives passed. That gives 3 half-lives. So we divide by 2 3 times. But the part of the radiation which is incorporated with background does not decrease with the same pattern as half-life. So first we need to remove the background. So 550, which is the initial value, minus 30, the background, that gives a value of 520. Then we divide 520 by 2, that gives 260. Divide by 2 the second half-life, that gives 130. And for the third half-life and the final one, 65 counts. But the reading on the detector would include a background, so we add the background again to the final reading. So 65 plus 30, that gives an answer of 95 counts per minute. Part D says, state 2 safety precautions taken when moving, using, or storing radioactive sources in a laboratory. So for using and moving, we can wear protective suits lined with lead. And for handling, we can use long tongs. We can also say for storing, we store it in thick lead containers or thick concrete containers or cupboards. But we only have 2 for the question. Question 10a says, state the equation that defines the average orbital speed v of a planet. State the meaning of any symbols you use. So the speed is equal to distance divided by time, but the distance here is the circumference of the orbit. So 2 pi r over t, where r is the radius and t is the orbit period or periodic time. Part B says, suggest why countries that are a significant distance from the equator experience significant temperature variation through the year. That is due to the tilt of the Earth axis, which changes the amount of exposure time to sunlight. So the tilt is either towards the sun at some time of the year or away from the sun at the other time of the year or another time of the year. When it's tilted toward the sun, there is high exposure time or long exposure time to sunlight. When it's pointing away from the sun, the exposure time to sunlight is low. That's what causes the variation in temperature. Part C says, fill in the gaps in the paragraph about a star much more massive than the sun. The stage that follows the stable state in the life cycle of the star is the red supergiant, since it is much more massive than the sun. It then explodes as a supernova to form a planetary nebula. This leaves behind a neutron star or a black hole. So these are the options. Part D says a galaxy is moving away from the Earth with a speed of 33,000 kilometers per second. The value of the Hubble constant is 2.2 times 10 to the power negative 18 per second. Calculate the distance from the galaxy to Earth. Give your answer in light years. So first we use the SI units, and the equation V is equal to the Hubble constant multiplied by the distance. So distance is equal to the speed divided by the Hubble constant. So we have 33,000 multiplied by 10 to the power of 3 for kilometers to convert into meters. Then we divide by 2.2 times 10 to the power of negative 18. That gives 1.5 times 10 to the power of 25 meters. And the light year is 9.5 times 10 to the power of 15. So to convert from meters to light years, we need to divide 1.5 times 10 to the power of 25 by the light year, 9.5 times 10 to the power of 15. That gives an answer of 1.5789 times 10 to the power of 9, which we can approximate to 1.6 times 10 to the power of 9. So this was the end of the exam. I hope you enjoyed this video and found it useful to you. I wish you the best of luck and keep solving more problems, and I will see you in another video.